This, so thank you, Julia, for your presentation. And today I want to present several results I recently obtained several months ago that they can be quite interesting. And we found we had a tour for me today to present it. It's a day out of work in Poland, but anyhow, I want to thank you all that they are attending for listening to me in this special day. So, okay. So as the talk says, this is an approach to jet bundles using K-contact manifolds. And what I want to show you that is quite interesting is the fact that all finite-order gel manifolds can be described. They can be not only described by, but characterized by means of a certain sort of K-contact geometry called polarized, higher-order polarized K-contact geometry. Yeah. So the thing is that these results allows us to do a lot of things by means of K-contact geometry. Essentially, it potentially could, as far as I noticed, there are many methods I will describe that can be recovered by means of K-contact geometry. Yeah. The first thing I will show you is that we can recover the Cartan distribution of finite order jet manifolds as a so-called K-contact distribution. Yeah. The result was known for the first order jet manifold locally by Narciso Román, Javier Rivers, and the co-workers. Yeah. But we will show that this was the one case. Yeah. And it can be extended to all finite dimensional finite order jet manifolds. The only thing is that to do so, a much deeper understanding of the structure of the associated K-contact distribution has to be obtained. But once this is reached, indeed by means of a distributional approach, and by using, instead of the K4 by means of the coordinates, by using a deeper understanding, we can recover essentially the Spencer operator. We can describe polarizations in terms of K-contact geometry, the differential, the vertical differential, horizontal differential, the bivorational cohomology approach for jet manifolds can be described by means of K-contact geometry. Yeah. And essentially, we, as much as I could see, all geometric structures on the finite jet manifolds can be described by means of K-contact geometry. Indeed, there is a new thing, is that since we describe jet manifolds as a particular case of K-contact manifold by means of the so-called polarized of Legendre-type of order R, which is how it's the technical result. As used this, jet manifolds are considered as a particular case of K-contact geometry, but K-contact geometry is much general than jet manifolds. And in this manner, techniques that they are used to study jet manifolds and PDEs that are linked to a particular jet structure by means of a certain independent variables of the higher order partial derivatives can be retrieved in a natural manner. I mean, what it was not natural in jet geometry, but it could somehow be described. What it was not natural in PDE is because you have to change the role of independent variables, or things like holograph mass, reciprocal transformation, vector transformations. They can be retrieved by means of K-contact geometry. One of the biggest advantages, as far as I could found, is that our reduction is not by means of prolongation of vector field. This is a very particular case. And when you reduce partial differential equations by means of a more general stuff, the thing is the reduced system can be characterized if it comes from another jet manifold. I mean, it can be described like a differential equation. That means another dependent and independent variable. So this approach, for instance, is very new because it does not fit naturally with the jet manifold approach. So, as I said, the talk is going to retrieve natural jet manifold geometry, the natural structures, yeah. And then what we are going to do is just extend them by means of K-contact geometry, yeah. Let us say that K-contact geometry. This could be. Okay, so I will continue by myself, then I will pass it. Or we have a problem, technical problem. I will continue. So the thing is, we start with fiber manifolds, yeah, with a figuration, and when we have the R fiber bundle over this bundle pi, you know that variables used in here, the differential structure, is by means of coordinates that they describe informally independent variables of certain sections of this manifold, and the consecutive derivatives that they characterize Taylor expansion of these sections out to order out. So one of the main structures that you have and jet manifolds is the Cartan distribution. The Cartan distribution is spanned in an adapted system of coordinates by means of two families of vector fields. One family consists of n operators. They are called normally that the total differential, there are vector fields that they play the role of the total differential of functions and functions on the holonomic sections of the manifold. They are in this manner, they are written. I is just a multi-index, you know, having n coordinates. It's one of these coordinates that describe the number of partial derivatives we are doing in this variable. Alpha is the index for dependent variables. I is the index for independent variables. And this total differential, the indexes, they have a weight or a module. I mean, the total number of partial derivatives that is less or equal to r minus 1. And this variable, as usual in the literature, is the multi-index I, where we are adding a unity, a 1, to the position I of the index. So it's like making a new partial derivatives on terms of the variable xi. So in the manifold, the jet manifold of order R, we have certain sections that are very important. They are the so-called prolongations of sections, yeah. And the prolongations of sections, they are characterized by saying that the tangent space is tangent to the Cartan distribution, okay? And the thing is, the co-rank of this Cartan distribution is given by this number, with m is the number of the dependent variables, yes, the order of the rank of this vector, of this bundle. N is the dimension of the base manifold, R is the order of the jet manifold. So this is the usual stuff. Now, when you have a 30 Cartan distribution, you have 13 operators that are naturally defined there, natural structures. One of these is the canonical yet structure for the R, that is a differential warp form on the R, on the manifold, on the jet manifold, the R, and taking values in this object. Yeah, this is the vertical part of the PR minus 1. This is the mapping that goes from the GR minus 1 onto the base manifold, yeah, and the vertical part will space with the vibration and pull it back to the total. Okay. The thing is, this thing can be understood in different manners, and it can be also understood that this thing, this is called the Spencer operator, is indeed an operator, and it looks like this, but it is different because you see here, you know that this is a differential waveform taking values in this vector bundle, and here in coordinates, they look both the same, in adapted coordinates, they look exactly the same, but the interpretation is different because here, the partial things that they here on the image, here they are understood at a differential. So this thing is understood to work on functions and give differential forms, differential one forms. So both things being in local coordinates the same, they are different things, okay? And then they use for different for different applications. Yeah. So it turns out that the kernel of this object is just the Cartan distribution, the kernel of this thing. Yeah. This expansor operator measures the value of tangent vector to prion to the tangent vector j r minus 1p described by the jet. Well, this is just a canonical, this is a way of understanding geometrically this operator. Yeah. For me, just think of it in this manner, that this is like a 1/4, the kernel, yeah, is the Cartan distribution. And as a differential operator is the expansor operator that it works for jet theory. Yeah, so there are two things that they appear in this theory. So the thing is that the K-contact formalist is going to recover these two things by means of a K-contact form. Okay, so let me just recall what is a K-contact, what is K-contact geometry. First is a generalization of contact geometry that appears as a particular thing. Yeah, so a K-contact form is a one form, yeah, taking values in RK. You can say that it has K forms, K1 forms, yeah. And the thing is, this is defined on U, it's a differential one form on U taking values on RK, yeah. And the kernel of eta is in direct sum with the kernel of the differential, and it gives the total space, yeah. That it gives the total space. And the thing is, when this happens, you can prove that the kernel of eta is a current K maximally non-integrable distribution. That means that there is no vector field in here, in this, that leaves distribution even at 13-point invariant. This is something that is quite useful, yeah. When K is equal to 1, as I said, this is contact geometry. When K is bigger than 1, the components can be used, can be described by means of differential force, standard forms. Yeah, this is the thing that Narciso, Roman Roy, Javier Rivas, and others did. Yeah, they call this indeed a K-contact structure, calling out this form. Yeah, and then there is something called the red direction. There are vector fields that they play the role in K-contact geometry, or the red vector fields usually play in K-contact geometry. There are vector fields, K, belong to the kernel of the eta, yeah, and they are dual to these contact forms, yeah, to these elements of the K-contact form, yeah. And it can be proved that they don't belong to the kernel of the eta because they are direct sum. So it's something interesting. Now, the thing is, this is the initial approach given by Narciso Roman Roy and Xavier Rivas and Jordi Casset and others, yeah, that they were focused on this K-contact structure, I mean, of these K1 forms. And they developed an extension of contact geometry to field theory. Yeah. So then, Xavier Rivas, myself, and a PhD of mine, we developed another approach, yeah, that it's not focused on the K-contact structure, but it is focused in the kernel of the K-contact structure, on the so-called K-contact for our lecture. So we define a K-contact distribution, yeah, as a distribution that locally around every point can be written as the kernel of a K-contact form. This was our idea, that K-contact force is something that can be described locally, yeah, can be defined locally, but we require them to be such that there is a distribution that can be described by means of these K-contact forms locally. Yeah, the thing is, for a same distribution, for the same D, this eta, it's not uniquely defined. There are different etas that can recover the same D, yeah? And if you have some differential one-fold equivalent RK and its kernel is D, it turn around that they don't need to be K-contact forms. Yeah? This is one of the things. But K-contact forms, or K-contact structures that is analogous, they are very interesting because they allow us to describe the K-contact distribution in a very nice manner. But one problem appears is that K-contact distributions, they are distributions that are locally the kernel of a K-contact form. But we wanted to describe this K-contact distribution in a manner that is independent of determining the K-contact form. We wanted to look for something geometrical to describe it. And this was solved by Ribas, Sobczak, and myself. And we described that a K-contact distribution, a distribution is K-contact, yeah? If and only if it's maximally non-integrable. Okay, it is said that Levi-Strauss has to be a kernel. I will explain afterwards. But the thing is, this notion is quite a standard literature, yeah? And around every point admits a local Reed frame. Reed frame, it means that there are K vector fields commuting among themselves and being a symmetry of the distribution. Yeah, this is the idea. This is what is here. There are vector fields, yeah, that they commute between themselves. They leave the distribution, the vector fields on the distribution invariant, and they give you a complement to the distribution, the K-contact distribution D. Yeah. The thing is, local Reed frames, there are lots of them. Yeah, or sometimes they are just one. It depends on the case. Yeah, they are defined locally. Yeah, and looking for them, well, it can be sometimes tricky. But the experience, our experience, that in many cases it's easier to get this local Reed frame than obtaining the associated K-contact form. But they are dual. I mean, when you have this eta, the K-contact structure, you can associate the Reed vector fields of the K-contact structure, and you get the Reed frame. Or the other way around, if you have the Reed frame, you look for a differential waveform, taking values in RK, that is dual to this, and boundaries of the K-contact distraction, and you get the eta. This is what we prove. Yeah.
One second. I was thinking that by the Frobenius theorem, you can instead just say that the Reed frame is a integrable distribution.
No, cannot, because it destroys the fact that you live invariant the distribution.
But I was going to say an integrable distribution such that every section of the integrable distribution.
The problem is that you can have an integral distribution, but looking for a family of vector fields that leave this one invariant is additional problem. Yeah, it's unfortunately. It's not that easy. When you have these functions and you multiply the Frobenius theorem, indeed, this expand an integrable distribution, yeah? And this is the basis. But the problem is that when you have the distribution, you have to look for certain vector fields, yeah, that they allow you to have the other thing invariant. And mixing them, it does not work. That's the problem. That's a problem.
Yeah, I see. Sorry.
Yeah, no. It's a good question. Indeed, we were looking, Javier, we were struggling with this thing for several months with Xavi and Thomas, trying to figure out if we could say something about that, but we didn't manage to do much. Yeah, it was a hard problem. The thing is, we are going to use this distributional thing to describe Cartan distributions as K-contact distributions. And the thing is, this works because for us, there was no manner to obtain the K-contact form associated to them, but there was a way to look for this because the thing is, look, this thing is maximally non-integrable, and you have to obtain a local Reed frame of symmetries. Yeah, this is easy. Normally, when you have the Cartan distribution and you want to describe some K-contact form that will give you this as a kernel, the natural candidate for this is the contact form, the standard contact form. These are not contact forms in the real way of precise meaning of contact geometry. They are contact because they are described by means of equivalent relations of contact of section up to a certain order of the Taylor expansion. Yeah, but the thing is, when you have a first order jet manifold, yeah, the contact forms, they allow you to construct straightforwardly a K-contact form. I mean, if you have the Cartan distribution and this R is equal to 1, you will have exactly K-contact forms in adaptive set of coordinates And these contact forces are indeed the canonical example used in polarized contact manifold. When you have a first order one jet per jet manifold, it turns out that the Cartan distribution has current K exactly. If the jet manifold has rank K, the Cartan distribution has current K, and these things, they give you the K contact structure, the K contact for the K contact structure. It's exactly that, And you have certain vector fields of these ones that were known by Narciso and all their co-workers and other people working on it. But when you go higher, these standard contact forms, they don't give you the K contact form. You don't give you something that it can be called K contact form in a natural manner. The thing is, you have to look for another idea to deal with it, and we will do it distributionally. The thing is, by the theory of distribution, the jet theory, that the Cartan distribution is maximally non-integral. So the thing you have to do to look for K contact forms to construct local Reed frames by means of Cartan symmetries, λ-symmetries of the Cartan distribution. You do that by means of our characterization. The contact forms, the associated contact forms will follow. They are NR pi contact forms because this is the co-rank of the Cartan distribution. So how it looks like, As I said, in here is that the usual stuff, you have the theta alpha I, there are these things, And as I said before, this thing, the kernel of all this stuff, they give you the Cartan distribution, but they don't define an NR pi contact form because if you put all those together, you try to do some NR pi contact form, and you put this as the coordinates of this, it turns out that, okay, the kernel is the Cartan distribution, but the differential is not in direct sum with the kernel to give the tangent to this. It does not work like that. Indeed, you can do an example. Here's an example. You have vibration, you have two independent variables, two dependent fields, two dependent variables. You pick up J2 pi. The Cartan distribution is the total differences in terms of the first variable and the second. And then you have the derivatives in terms of the variables of higher order. You have that this has 6, 8 has rank 8. The dimension of the true jet bundle is 14, so the co-rank is 6. And you have 6 Cartan forms indeed. But when you do this Cartan form, the standard Cartan form, you work out the differential. The kernel has only dimension 2. So the dimension of the Cartan of this candidate to Cartan form with the differential is just 10, and so it's not the total space. No, it does not work. But here comes the nice thing. Let us describe a Reed frame. We are going to have, indeed, here you see 6 vector fields. And here they seem to be arbitrary, but they are not. They are just vector fields that are defined on the base manifold E of the J2 pi, and they are prolongations of vector fields on E to the total manifold. Here you have just the partial derivatives in terms of dependent variables, and here you have this, but you have each one of the coordinates, base coordinates. So these vector fields, these initial ones, they are prolongated to the total space. When you prolongate, you have this first 2 vector fields. When you prolongate this, you will have 4 vector fields, and this is the prolongation. So when you have this, since the derivatives you get of the higher order, up to 1 here, they have coefficient 1. They are linearly independent. They are symmetries of the Cartan distribution because they are prolongations of vector fields, and they are λ-symmetries, and they commute between themselves because they are vertical. The coefficients depends on vector fields on the base, and the partial derivatives, they are just with respect to the fields Q alpha, the dependent variables of derivatives. So they commute between themselves. So this means that this structure, if you pick up a dual, you will have this thing that it is indeed a 6 contact form. Yeah. So you have described the Cartan distribution as a 6 contact form, and the red frame is given by set vector fields given in this manner. And this is just in the case, yeah. But there are more things that they are interested in here. Yeah, you have the so-called Riff lift that for every element of a base of R6, they give the vector fields. If you compose both of them, and you make some calculations, you get this. But these coordinates and understood in a proper way is the Spencer derivative, the Spencer operator. When you do derivation here, you consider that you are derivate and you to the result of applying of function you can one forms. But if you understand these like one force taking values in a certain bundle, it is the canonical structure on J2. So everything fits. The canonical structure on the J2 pi has indeed the number of coordinates of the perfect contact form. So you have to understand the Spencer operator of the canonical structure in a manner that it turns out to be a K contact form, with K being the NR pi. So this is an example, yeah. Also, it's interesting that this thing in coordinates is the vertical differential of order. So it turns out that this composition essentially is the vertical differential. So you will have an horizontal differential, you have a total differential, you have a total bicomplex, yeah. So you have obtained everything in here, and there are more analogous, yeah. So our theorem is that the Cartan distribution CR pi and GR pi is an R pi contact distribution where the number of the key is just given by this and is fixed by means of the jet bundle. So as at every K contact distribution is maximally non-integrable. Yeah. In every rapid cart, we have the local refrain that is transverse to CI pi. Yeah. And the associated contact form, K contact is NR pi contact form has CR. So how we construct the local refrain? The local refrain is given by this expression, or more essentially by means of this. You have every dependent variable U alpha, and you pick up polynomials on the base manifold given by the J, okay, the multi-index up to order R minus 1. These are prolongations, so they leave the Cartan distribution invariant. They are vector fields with coefficients that depend on the basis, so they commute between the cells. And the number is exactly the one that gives you the corank of the Cartan distribution. So this is exactly the complement you're looking for the counter distribution. And when you consider this, that you do the dual, you take an NR pi contact form. So you have the distribution, and by using these reps, what you obtain is that all Cartan distributions for every finite dimensional fitting all the jet manifolds are things that are K contact distribution. They can be described by means K contact geometry. So you have described as a particular case the essential structure of jet manifolds, and you can do even more things. This is the sketch of the K contact theorem, but the idea is that CRP is maximally integrable. This is known. The RG alpha commute and process here because they are prolongation of polynomial vector fields on base coordinates on E. Yeah. These identities, they allow you to say that they are linearly independent and they give you a local frame. So it's more or less the idea. It's quite technical in certain moments. But the idea is easy, and we have lots of examples by now. So it's been proved for many things. Yeah. So if you want to see how the NR pi contact structure look, the coordinate expression is given by means of this, and you see that these are 13 non-trivial combination of the contact forms, the usual contact forms. Yeah. We like to use all these elements, all the NR pi contact form together, because only when you put it all together, you can then to apply the rev-lefts and other stuff to get the Spencer operator, the canonical structure of the jet manifold, and to differentials and things like that. But anyhow, that doesn't change the fact that as done originally, knowing these things in particular cases is a no. Yeah. Also, you have to take into account that this is local. This is just defined for adapted coordinate system jet bundle. You have another one, you will get another stuff like this. Another one, they are not equivalent. Yeah, they don't give exactly the same structure. But when you combine with the red lefts and you understand this properly together, they are geometrical. They are. I mean, the NR pi contact form is locally defined. Yeah, it's not intrinsic. In coordinates, by a means of appropriate understanding, they retrieve the Spencer operator, the canonical structure on the GR pi. Yeah, but you have to do additional stuff to obtain something that it will be intrinsic. But the idea of the Cartan distribution as a K NR pi contact distribution is totally intrinsic. Yeah, one of the ways of doing this intrinsically is consider the rep Spencer operator. Yeah, combine it with this, and this gives you the Spencer operator or differential operator log. Yeah, that's that. If you understand these vector fields as a section on the quotient bundle of the total space with the redistribution, you get also the canonical structure. So there are more things that are quite interesting, and is that there are some called Spencer contractions. The Spencer contraction can be described by means of the NR pi contact form. You pick up the eta, you pick up the differential, and now there is one thing very important here, because we have to unveil the whole structure of the Cartan geometry. So you pick up the Cartan distribution, and there is something natural when here there is a distribution, that there is a way of dividing this locally. This thing here is global, is something well defined, is the kernel of T pi r minus 1. And the other thing is this thing. This is also bundle locally defined by the total differential. Yeah. This is something that is intrinsic to jet manifolds. Yeah. And when R is equal to 1, this thing is the usual notion of a polarization given by Narciso and Xavier. Indeed, in first order manifolds, jet manifolds, the dimension is m plus n plus m plus n, and this dimension m times n is within this distribution that is m plus n plus n. Yeah, and not ground, so everything fades. This is just a generalization, a quite not trivial generalization. So imagine that you have the differential of this of our NR pi contact structure. You feel the lift. And you compose with things belonging to this horizontal space and this vertical space, you say, yeah? When you do it, the contraction is something that takes values on the partial derivatives of order r minus 1. And here, there is a nice way of composing the coordinates of A with the coordinates of H. And this way of composing is called the algebraic Spencer contraction. It's part of the jet structure in some books. And essentially, this mapping that is tensorial, okay, it does not matter. This is a vector field, this is a function, but this is a tensor, gives you something that goes in the tangent, because this thing locally is like tangent to Q, yeah. This thing can be isomorphic to the symmetric tensor product of the cotangent of Q times the vertical pi to S r minus 1. This is just technical. I will not go into details, but this is a Spencer contraction, and is divided by means of the key contact structure. So, summing up, the Cartan distribution is an NR pi contact distribution, standard contact of prey, so not adapted generators to the annihilator. If you adapt them, you will obtain the NR pi contact form. An adapter ray frame, they are transverse commuted Cartan symmetries. Yeah, the Spencer operator is the composition essentially of our contact form with the red lift. The Spencer contraction is just the differential of the NR pi contact form with the red lift. Yeah, and you can go on and go on and go on. So, yes. Now we, in this part of the talk, after showing that every JR pi bundle is just a case of K-contact manifold, yeah, we will characterize jet bundles as a particular type of K-contact manifold. So the rule of this is just to say when a certain K-contact manifold as a manifold with a distribution that is K-contact, it is indeed locally at 2D homomorphisms, something like looks like a jet bundle. Yeah. So to do so, you have to remember that in the first order jet manifold, you have something canonical, that is the polarization, the tangent, the kernel of the tangent space to the P10. Yeah, this is the vertical towel, the highest vertical towel. This is called normally in jet geometry. And the thing is, this was a polarization. The polarization found by Narciso, Xavier, and collaborators in the first order case. To extend this to higher order case, we have to define a new type of polarization, more general, because the polarization by Narciso and Xavi and Jordi and others, I don't remember exactly in which works they were defined. They have a problem that they require you to have particular dimensions. They are fixed in a manifold particular dimension. They have a rank fixed. We have to drop this. We don't want to talk about fixed manifolds of a certain dimension. Yeah. So the thing is, in K-contact geometry, we have a notion of Legendre, we have orthogonals and things like that. And the way is the usual one. When we have the differential of the contact form, yeah, of the NR pi contact form, we have it as a differential. And when we have a certain subspace, we can look for the orthogonal, all the elements that vanish on it. Yeah. So in this manner, we have a contact analog of the symplectic orthogonal. So in the usual way, when the orthogonal is bigger than the original space, we say that the subspace is isotropic. When we have an isotropic and a complemented isotropic, we will say that it is a Legendrian. Yeah. And there is a notion of coisotropy that is more difficult, yeah. And the thing is, polarization in the sense given by Narciso, they are Legendrian. It can be proved. We prove it. I think that with Xavier and Thomas Sobchak, we did it. And in general, a polarization in the K-contact manifold is an integrable Legendre subbundle of the K-contact distribution of maximal rank among all integrable Legendrian subbundles. So you have to consider Legendre subbundle, yeah, as I said in the usual way of contact geometry, and it has to be integral, yeah. And not only that, you have to ensure that there is no other with larger rank. If you do so, what you obtain is that the highest vertical tau of the jet manifolds is a polarization in this sense. Yeah. So it's a particular type of polarization in this sense. And this is a nice result. In the case of R equal to 1 is just what Narciso and other people did. It's just a particular case that extends to a general thing. So the thing is, in the case of jet manifold, we have more things apart of this polarization. On GR0, we have this. G0 is a distribution. This is the kernel, as I said, of TPR to R minus 1. Yeah. And then you have all that are for S bigger than 1. Yeah. This case is for S equal to 0, and you can obtain this for 1 to 1. And this distribution is the kernel of the PR, the projection of the R manifold onto the base. So when you have these things, these structures, they are very natural in geometry. You have the coefficients. They are of this sort. They can be described by means of a bundle of this sort. And when you consider the total differential, yeah, and they act on these partial derivatives, that this gives you a basis of every one of these spaces, yeah, it turns out that they reduce the order. So when you have this here, where every partial derivative in terms of coordinates u alpha A of this, they have order, in this case R, and you make the total differential with this, they lower the bound, yeah? And you obtain things like that. So this is important because it's something important in jet bundles. If we want to describe jet bundles, not only we have to think about this as a polarization, we have to see that this polarization has another things that they are related to that, yeah? We are going to do is just to give certain polarizations of certain kind that, with conditions that can be checked, and we will give us when a certain polarized K-contact manifold is locally adjacent manifold. So the thing is, first, this polarization has to be split. This means that it has a complementation integrable. This is what I mean. In general, it does not happen. There are counterexamples in a paper that will appear on Monday, that I will send, where you have a polarization in the sense I gave, and there is not integrable complement. But it's something that it can be checked, okay? So this polarization is called to be of the Spencer type. When you put up the derivations of this Cartan distribution, this contact manifold, that means you pick up the vector field taking values in here, and you do all the Lie brackets 1, 2, and so on, and you obtain the derived series, and it turns out that when you do this coefficient, you obtain something like in the Spencer contraction, but with another order. So we say that this polarization is of the Spencer type. If when you work out this, it's easy to obtain. You obtain that these spaces, they are isomorphic to this, and the polarization is isomorphic to this. This was what we obtained previously for the case of the highest order tower is the kernel. It was here for this, yeah, we're trying this thing. But for the derived series, you have to have these isomorphisms. This is easy to obtain, yeah. When you have a distribution, a K-contact distribution, it's easy to obtain. Well, it's a little bit tedious for calculations, but it can be obtained. This can be obtained, it appears, and this coefficients can be obtained. It can be seen if this is exactly this thing, something of this sort. And finally, you have something that is called a jet-type polarization. A jet-type polarization is that it's a split. It has an integral isotropic complement of P in the distribution. Now, there is an integral complement of this H in Tm, yeah? And when you pick up these things, this new S, yeah, it turns out that these spaces, okay, the action of H on these spaces in a certain manner, they recall the Spencer duals, yeah? This is, let me recall it. This is a split. This polarization contact manifold is jet type for the R if the polarization is split. It has an integrable complement, yeah? You have a Spencer type identification of the graded coefficient. I mean, this thing and this, okay? And finally, you have an integrable complement of H, and you have this distribution that they are involved. This is the stuff, yeah? And these things, they characterize a jet bundle. If you have these things, you will obtain a jet bundle locally for your initial K-contact manifold. So the local recognition theorem tells you that a polarized K-contact manifold is of type another R if and only if locally around every point there is a certain morphism, this polarized constant morphism, this is technical stuff. The only thing is that there is a change of variables that maps these things into a jet manifold. The M is locally diffeomorphic to a jet pi. The D goes to the Cartan distribution. The polarizations goes to the JR pi, to the polarization. Okay? This is the thing. If it's of jet type, it happens. If it does not, it does not happen. So locally, what it says is a Darboux theorem that says if this is of jet type, you will have coordinates in which the coordinates of n, they are the coordinates of a jet manifold. The distribution there has a basis given for the typical one of the jet manifold, and the polarization, it is that those of a jet manifold. So it's a generalization. When Narciso gave the K-contact Darboux theorem, it's just a theorem that tells you that locally polarized contact manifold was a jet of a bundle of first order. And this gives you the general stuff. You can do this globally, but this thing is quite technical, and I will skip it and how the version. And I will tell you that once you do this, what we have now, is that we have retrieved the whole jet theory, and we have characterized when jet manifolds come from manifolds that are K-contact. This is the thing. The thing is now the properties of jet geometry can be retrieved by means of properties of K-contact geometry. For example, it can be proved that the extension of a jet manifold to the following one, it can be recovered by taking the Cartan distribution and taking the description of all the Legendrian subspaces belonging to the Cartan distribution. If you do that, in K-contact setting, it turns out that this manifold is exactly the following prolongation. So, what it means, this result, is that the prolongations in jet geometry is a Legendrian prolongation, the K-contact geometry. When you have a PDE is normally a submanifold of GR pi, and the thing is, when in the theory of differential equations, you normally have to prolongate these differential equations to deal with stuff, doing certain things. And when you can prove is that under very general geometric conditions, the only thing you have to do at every point of the submanifold is to look for Legendrian subspaces tangent to the manifold. If you do that, you what they want. This is called the Legendrian extension of the Cartan with respect to this one. You obtain the usual stuff. Holonomic sections. They are the so-called polarized Legendrian submanifold. Yes, it's a lot of terminology. Yes, let me tell you that in this talk, because it's a lot of things to say, too much to say. The thing is that the holonomic section, they are prolongations of certain sections. They are just submanifolds, that they are contained in the Cartan distribution, and they are a complement to the vertical tower. The thing is, in K-contact geometry, they are understood as submanifolds that are Legendrian, and they are tangent. I mean, they give a complement to the polarization. This is the idea. Okay, so yes, let me skip something. Well, the principal symbol can be described. Let me just tell you several things that can be interesting. Okay, so let me move to one of the nice things here, and the characteristics. This is nice. Okay, so the thing is, in K-contact geometry, when you characterize jet bundles as K-contact manifolds, the prolongation of vector fields, the evolutionary vector fields, they become Hamiltonian vector field related to the K-contact extraction. This is the nice thing. They are Hamiltonian vector fields, and as such, there is a manner to relate them with a Hamiltonian function. That it is Hamiltonian is a function valued on a third-time vector space, and is given in this manner. So when you have a vector field, it's Hamiltonian. That means essentially that it lives invariant the K-contact distribution. When you contract with our NR pi contact form, you obtain a Hamiltonian function. That is a function given with values on R pi. So the thing is, this Hamiltonian function has several coordinates, many of them. So when this vector field here is indeed something that it is a prolongation of a vector field, what it happens is that the Hamiltonian functions can be described by means of the differential, in terms of several variables of several finite number of functions given by this. And in differential equations, we know that these functions, they are the so-called characteristics. So it turns out that prolongations of vector fields are Hamiltonian, because in K-contact geometry you have Hamiltonian, and this Hamiltonian comes from the characteristic. And not only that, characteristics can be retrieved by means of our Hamiltonian. Indeed, the characteristic, these things of the Hamiltonian, allows us to describe the K-contact vector field was used to describe them. But this is just a particular case. I mean, in differential equations, we have this prolongation, the evolutionary vector fields, and all this stuff. And for that, they are characteristic, they are brackets of characteristics, and all this stuff can be retrieved by means of the brackets that exist for these functions in K-contact geometry. So everything we have is a particular case of that. Another thing is that, for example, when you have a third-time vector field and you have this characteristic, when this characteristic vanishes and all the differential of this characteristic vanish, we have an invariant subset. But this invariant subset is just when the Hamiltonian function associated to this vector field vanishes. So several theorems in differential equations, when we look for invariant subsets of a vector field, they can be retrieved like the 0 points of a Hamiltonian function. In generality, if you have a finite algebra of Cartan symmetries, prolongation vector C, the evolutionary of a vector field, these are, from the point of view of the K-contact geometry, Hamiltonian, and the Hamiltonian are essentially this contraction. So when this contraction vanishes, when all these functions vanishes, you have something that is called the Loci of the algebra of vector fields, and this is invariant. And the thing is, this is something known in differential equations, but here it appears simply like a result of K-contact geometry. Indeed, it can be understood as a Marsden-Weinstein reduction in K-contact geometry. What it was developed by Bartosz, Xavi, Silvia, I think, and myself. Yeah, but we are working on that. Yeah, the thing is also that all this stuff can be much generalized. Okay. So let me explain to finish. Yeah, because here there are, as I said, there are many topics, many things. Maybe I tried to explain too much. I wanted to give just an overview, and I didn't have to prepare this much. The thing is, what we did before was just to retrieve what it was done previously, or this in jet geometry, some of the stuff can be, there are many other things. Yeah. And our extension thing is that since K-contact jet manifolds, they are a particular case of K-contact geometry, polarized, is characterized, yeah, we can extend things. We can, the methods of jet geometry, to extend them to a wider framework, work in that framework, and try to go back to jet manifolds again. And the thing is, the possibility of going from jet geometry to K-contact and back gives you techniques that they are far of being natural or allowed or easy to obtain in jet manifolds. And one of the results I found very interesting is that we can do a reduction, but of a reduction of partial differential equations. But the nice thing of the reduction is that it's not anymore by means of prolongation of vector fields or contact transformation or that. These are particular cases of this theory. This is in a paper I will show how to retrieve it. The thing is, we can go much further. We don't need any more Cartan symmetries. We don't need any more prolongations of vector fields. This is much general. We can even forget about vector fields that they leave invariant the Cartan distribution. It's not needed anymore. So what I developed was a method of the reduction, and this method of reduction goes like follows. We have a Lie group, yeah, And we have the distribution generated by the fundamental vector space of the Lie group action. Yeah? This group is not going to preserve the CRP, the Cartan distribution, anymore. Yeah, so it could, but it doesn't need to. So what we are going to do is that to ensure that when we have the Cartan distribution, this distribution plus the distribution generated by the fundamental vector field, this is invariant. We don't need to the tangent space to the set of solutions to be invariant. We require that this thing with the distribution of the Lie group, it will be invariant. We don't require the polarization of higher order this of jet type to be invariant. We just be invariant this space. If you do this, you can reduce the differential equation, you can reduce the jet manifold, and you will lead to a new manifold with a new distribution. But now, and this is the nice thing, you will get some reduction of the K-contact distribution. The original and the K-contact distribution is the Cartan, for example, and the GR5. But now, this thing, when projected, they will not have in general any relation with the original jet bundle, nothing. But you have the recognition local theorem, the theorem that tells you when this thing and this thing, they come from a jet manifold. So under very general conditions, you can see that the reduction of this and the reduction of this, yeah, they retrieve again a K-contact manifold with a polarization of jet order, of another order, probably, related with another different jet manifold. So you see, the generality is such that you start with a differential equation in a jet manifold, you reduce, you magically have something, sorry, maybe, we can reduce it, yeah? And the final stuff is because a new differential equation is something absolutely different. And our theorems allow you to describe it like a new jet bundle. And if you apply this to partial differential equations, for example, we did it with PDEs, it turns out that you are able to describe new PDEs. Yeah, and this is the very general stuff that we have. More things, we have Beckman transformation, Lax-Pers, orthographic transformation that makes the role that dependent independent variables, they don't fit very well in the jet manifold structure because they change the structure of the manifold. They can be understood as key contact transformation. There are other many things that they can be done. And yes, there is a lot of things to say. I hope that at least the main things were clear. I hope that it was interesting. Thank you very much for your attention. Hello?
Yes. So are there any questions?
Okay, is it that no?
There is some comment on the chat. I don't know, but it's...
Yeah, it's Narciso that had to leave. He said that he had to leave. So, okay, so
okay. Thank you, the speaker.
Thank you for listening to me, and bye. Michał?
Yes? I have a question to you. By the way, you have the reduction of K-contact transformation. Is it this reduction? It's a simpler system that you obtain.
In certain, Michał,
you reduce the original one.
You reduce the dimension of the manifold. This is the simplification, and you drop out certain. You recover some symmetry, original symmetry. So, in general, the answer is yes. But you don't know. What you are sure of is that you remove something like symmetries of the system, and the final system it will be a manifold of lower dimension. Yeah. So normally it's easier to deal. I applied this to KdV, for example, yeah, I calculated the breaks, and I applied this to other famous differential equations to recall, for example, Lodograph transformation, things like that. And it worked well in the sense that transformations that they are obtained magically in papers about these PDEs, here they appear naturally. I mean, there are, for example, no contact transformations, or there are transformations, the Lodograph, or things like that. When you apply this scheme, yeah, and you obtain the reduction, in the reduction, the theorem tells you how to choose new variables. When you choose these new variables, they mix different, for example, third-order derivatives, or they mix dependent variables, and you obtain what it was known. This is what I can tell you. But if it's useful in new example, it's something that it has to be proved. I don't know.
When you said that you use the Lodograph transformation, you have to have the same number of dependent and independent variables because you linearize.
Yeah, I mean, you have restrictions on the final manifold. Yeah, let's say that. But for K-contact geometry, that is not a problem. I mean, the distribution, you pick up one transformation that goes from one K-contact distribution to another. And now in the new one, the thing is, these are variables, they are mixed. Yeah. And the transformation is such that it tells you, now, listen, these dependent variables, they will be independent ones. These independent will be dependent ones. And in the new thing, you will have a jet bundle. Yeah. So in the final manifold, to have a jet bundle, these conditions that they are the local recognition theorem, they tell you that the number of independent, they cannot be changed arbitrarily. They must fix in such a manner that you will have new independence and new dependent variables for the ones you have. So it appears normally. It appears as a condition of the recognition.
Could you use the Legendre transformation?
Yeah. Indeed, it's a very nice example because it's not that example that keeps the structure of the jet manifold. It's a mix of the coordinates. And I will, the preprint I have prepared, it has as an example a Legendre transformation. Yeah, it's an example where the jet structure is normally destroyed, let us say this way. Yeah, but the K-contact structure survive. You pick up the K-contact, you make the transformation, and when you finish, you say, does this comes from a new jet manifold? And it turns out that in general, the answer is yes. It comes from, so it works. But another one.
One last my question. You have the characteristic of the vector fields, which was denoted by Q. Yeah. Could you do this defect structure? How it is how it is done for partially invariant solutions?
I haven't done it.
No, and this is maybe it would be interesting to look at it.
I'm open to questions. The thing is, I have a formalism. I have a couple of examples for everything. I know that it's quite new. I think that it's quite
it's
general
suggestion.
Yeah, but I mean, the thing is, which parts of this has worked? I mean, what it could be done. For example, I didn't talk about it. But when you have lambda symmetries, for example, what you do is you pick up the jet bundle and you extend it by means of a vector space. And in this new, you have a new K-contact transformation. And lambda symmetries, they are K-contact vector fields of this new one. So doing this stuff, you retrieve the work by order, for example. But I didn't get any example. I don't know if this gives you something new. Theoretically, it's nice, it's cool because it tells you how it comes and it gives you a common language. But I would like to know, or to ask someone in which examples I can apply this that practically, not only theoretically, they can give you some advantage. This is the thing.
This is related to the rank of this characteristic vector field. So if the rank is 0, 1, or 2, you have some characterization, and it is interesting to pursue. Maybe
I will send you the preprint. Tell me.
We will talk about it.
No, indeed, it will be. I'm very pleased that you can tell me something. Yeah, I didn't talk about Riemann invariance. It seems that it's something. But we will talk about it. Yeah.
Yeah. Okay.
We have lots of things to talk about.
Thank you for your talk.
Javier, I'm sorry. Yeah. Also a question. So in fact, this means that you can describe geometrically, for example, usual even reduction, Lie reduction.
Yeah, it's a very particular case. Yeah, it's the simplest case.
Because, for example, I know that for example, in Olver textbook where he tried to describe this Lie reduction more geometrically on jet spaces, so there are some gaps in this like consideration. So do you avoid these gaps somehow? Yeah.
I mean, the thing is, Roman, I didn't check the standard literature because this gives you something that is very different. I mean, I can compare this with jets, yeah, but as I said, jets are a particular category of K-contact geometry. So normally what I do with all this stuff to make it more general is that I put something that is on jets, I put it in the K-contact category, I do my stuff in K-contact geometry, and at the very end, the recognition theorem is applied to know if this goes back to some jets. Essentially, what it means is that in the middle, all this usual stuff for jets and reduction, they are not seen. It's difficult to compare. Yeah, I have compared with a couple of examples because the paper I wrote, it has 60 pages, and I had to cut something. But if you know where are things interesting, I mean, as you said, there are several gaps. Yeah, if you could tell me the work where these gaps were, I will try to see how I can overcome it, or where I overcome it. Yeah, how I did it. But you know, the thing here is that these vector fields is that they don't keep the Cartan distribution invariant, so they are not. They are not prolongations of vector fields. They are not Cartan symmetries. So if there is something related to this Cartan symmetry or whatever, it was lost into this thing goes away, yeah, and then goes back. So in the middle, it does not need to be attached. Maybe I just skip it in another different manner.
Yeah, and one more question is about differential substitutions. Yeah, so it's also possible to describe differential substitution by this language.
Yeah, but this is you know, I have been trying many extensions of this thing, yeah. So I think that it is possible, but I should work on it. I mean, differential substitutions, for example, the theory of ideals and Cartan theory, and with differential, for example, like I am still his name. I forgot. I don't remember some name now. Michael Phelps and all these people. I tried to go through it. I tried to discuss all this stuff. I think that I could do something, but I'm not sure now. That I think possibilities. We have possibilities, but it's too much for me. It's too many things. I don't know. Indeed, this talk, it was partially to say, see, I think that this is worth it. It can be interesting. It has many applications. Use it, or tell me where it will be fun to in which way. Yeah, what can be interesting. I don't know what is most worth.
Okay, thank you very much. Yeah.
Thank you, Roman.
Okay, are there any other questions? I think no. So thank you for a nice talk, Javier. Okay, so next week we have Adam Mascalanec, and whose talk will be announced in the following days.
Okay, so thank you, everybody, and Michelle, we'll be in touch. See you.
Yeah, we'll be
next
in touch.
Week.
Yeah,
no, next week. No, in 2 weeks.
In 2 weeks.
From now. Anyhow, I will send you this and let me know what you think that is worth it, and it will be nice.
Okay.
So, thank you. And also, yeah, thank you. Bye.
Bye.